I'm Christine, and I'll be talking about model selection and overfitting. So basically, if you don't know how to evaluate your models properly, there's no point to anything we do. Okay, so I'm going to start with a little quiz, and I want you to look at these two linear regression models and try to tell me which one you think is better. I think you haven't learned it yet, but R² is basically just a metric for linear regression, and generally higher is better. So, any ideas?
Yeah, it's on the right.
Okay.
Actually, can I?
Yeah.
The right seems better, but it's better for this type of thing. So if you put another start in front of it, it's gonna be.
Yeah, so basically what she said is this one on the right is better, but only for that specific data set. And if you gave it new data, it probably wouldn't predict very well. And yeah, that's exactly what we're trying to show. So basically, both of these models are pretty bad. So in this SLU, as I said, we'll be talking about how to evaluate our models. And as we saw on the last slide, it's more than just maximizing some metric, because we also need to make sure that our models generalize well. Okay, so a quick overview. We'll be talking about the bias variance trade-off, how to split your data, and then something called regularization for linear regression. Okay, so there is a trade-off between these two things called bias and variance. So basically, in any supervised machine learning problem, we're trying to learn the best function that takes you from X to Y. But that's for all of our data, not just for the data we have now, like data we'll receive in the future, because let's say our model's in production, we're getting new data from clients. We need to make sure that our models continue to perform well on data we haven't seen before. So two ways we can kind of measure this, or measure the problems with our model, is something called bias and variance. Basically, if you look at these bullseyes, high bias is you just kind of always miss the mark. Your model's learning the same wrong thing. And this kind of comes from models that are too simple or not strong enough. And then on the flip side, we have variance where your data is your predictions are far from each other. So you could be fairly accurate. Like on the top right, you'll see maybe if you average those, your predictions look pretty good, but there's a wide variance among your predictions. And we can kind of say that's the model learning random things. And that comes from models that are way too flexible. So again, we can go back to our regression example. We'll see that the first one on the left is an example of high bias, or something we call underfitting. And then the right model is high variance or overfitting. And I think underfitting and overfitting are kind of self-explanatory terms. One way you can think of overfitting is your model memorizing the data it's seen already. So yeah, sorry, what's your name? As Elena said before, if we received new data to predict on for both of these models, they would perform pretty poorly, even though the one on the right looks pretty good if you just look at the metric. Okay, and this is a pretty important concept because it's agnostic to any model or algorithm you use for supervised learning. So here's an example for classification. You have high bias on the left, where you have a lot of misclassified examples, high variance on the right, where your model's basically just learning noise, and then in the middle, you have kind of the just right model. But you'll notice that even the just right model still isn't perfect, and that's okay, because in real life, your data has noise, and we call that irreducible error. And actually, the fact that this kind of error exists is a really good reason why you should always start with a model that is simple and quick, because if your data is just unlearnable for any model, there's no point in wasting time training something really complex. You should just start with simple baselines and then iterate from there. Okay, so again, there's a trade-off between bias and variance. In theory, you want to minimize both while we're also minimizing error. It would be great if we could just take some derivatives, find the minimum, and everything would be great. but in practice, that's not possible. So the only way to do this is really through trial and error, experimentation, and testing. So that brings us to the next topic, which is train and test error. So basically what we do is to kind of fake the model seeing new data, we can split our model into a train set and a test set, and then measure the error on both. So the training error or in-sample error is, well, how well the model performs on the training data, and then the testing error or out-of-sample error is how well it performs on new data it hasn't seen before. Okay, so the most basic way to do this is something called train-test split. And sklearn has a method for this, which you'll see in the examples and on the README. But basically how it works is once you get your data, the very first thing you should do is split it into training and test. And then put the test set aside, don't touch it until the very end, because you don't want to bias your model to data outside of the training set. Yeah, so usually the training set is bigger than the test set. For test sets, I'd say generally 10 to 30%, but it's not a hard rule. And then, yeah, so you train your model on the training data, test it on the testing data, and that final test evaluation should be your sort of out-of-sample error. Okay, and then a slightly more complicated variation of this is to add a validation set. This works well if you have a lot of data or if you're trying to choose between one model or another. So what you do is you do two splits into 3 sets. Train, validation, and test. And then you'll train your model on the training set, validate on the validation set, kind of go back to the beginning. You have a new model, train, validate, and then when you finally think you have the best model, you then evaluate it on the test set, and that's your out-of-sample error. Okay, and then a third way to do this is k-folds cross-validation. So I think it makes more sense if you look at the diagram. So let's say your whole data set is the white and orange. To kind of fake having additional test sets, you split your data into, in this case, 5 folds, where you're training on the white data and then evaluating on the orange. And then at the end, you'll take the mean of whatever scores you're looking at for all of the orange sets, and that's kind of an approximation of the out-of-sample error. And this works really well if you don't have a lot of data, because the random split of train test might not be enough to capture like the full variance in your data set. Okay, so again, quick summary, we have train test split, very basic, train validation test split, and then cross-validation. And then finally, we'll talk about something called regularization. It's basically a way, well, it does a few things, but most importantly, it helps prevent overfitting in some cases. It's good to use if you don't have a very big data set or you have a ton of features and you kind of need to narrow those down. It's a way to kind of automatically pick the best features. Yeah, and another important thing is that it kind of creates another trade-off with this time between your model being well fit and your model being complex. Okay, so here's another set of linear regressions to kind of give you an intuition. So let's say we're trying to train a linear regression model to fit this orange curve. We see that it's a curve. We think, okay, we probably need something polynomial to capture that, but we're not sure to what degree polynomial is the best. And one thing we could do is just say, okay, we'll loop through polynomial of 1 through 200, and then just see what's the best at the end. And like, that would work, but it also takes a really long time. So what's really cool about regularization, it gets you this middle prediction without having to like do all of these loopings. It kind of is a way to automatically pick the best features. Okay, and so here is how we actually do that automatically. You end up adding a extra parameter to your loss function. Because the idea is, while you're training, you're trying to minimize this loss function. So if you want to minimize model complexity, you add a parameter that represents model complexity, and it automatically also gets minimized. So this is the L2 loss specifically. It's this like right side of the addition sign, and it's all it is just the square of the coefficients added up times some lambda, which is a parameter you set. It controls how strong the regularization strength is. And then you'll notice on the left side, that's just your normal mean square error for linear regression. So the left side represents like goodness of fit. So if it's low, you have a well-fit model. And then the right side represents complexity. So if that's low, your model is simple. And ideally, we kind of want both to be low. Okay, so L2 loss is used specifically in ridge regression. Yeah, again, sklearn has implementations for all of this, which you'll see in the examples. But basically here you have a linear regression model and a ridge regression model fit to the exact same input data. But you'll notice that on the right side, it's way less overfit. And if you actually plot the coefficients, most of them on the right side are 0. And then finally, there are 2 other kinds of regularization. There's LASSA, which uses the L1 norm. And all that is instead of squaring the coefficients, you take the absolute value. And then ElasticNet is the L1 plus the L2 norms. And it's just kind of like a best of both worlds. But you'll notice in that one, you have 2 lambda parameters that you need to set. And if you look at the plots, you'll see they basically do the same thing as ridge. So it's a bit of experimentation that lets you pick what's best for your data. So finally, quick recap. We talked about bias and variance, underfitting, overfitting, how to make sure that your model's generalized. We do that by splitting our data. And then finally, what regularization is. It prevents overfitting and growing model complexity. So yeah, that's it.